Welcome, learners, to the Explainer. So if you're staring down a physics exam right now and feeling, honestly, completely overwhelmed by spinning objects, tumbling blocks, and all those crazy angular vectors, well, you are in exactly the right place. Today, we're transforming this explainer into your definitive, high-yield study guide to finally conquer rotational mechanics. We're going to decode the physics, simplify those notoriously tough derivations, and give you the exact conceptual tools you need to crush those tricky exam problems. To lower your anxiety right off the bat, let's just break this down into 5 really clear steps. First, beyond the point mass. Second, the taxonomy of motion. Third, the physics Rosetta Stone. Fourth, key formulas explained. And finally, advanced decoupling. Okay, let's jump right into section 1, beyond the point mass. We're going to start by abandoning the safe, perfectly theoretical world of basic kinematics you're probably used to. Up until now, your physics journey has probably relied on a really comforting simplification, the point mass. You know the one. It's infinitely small, has 0 dimensions, and it's absolutely perfect for basic equations. But real objects are extended bodies. They're systems made up of infinite particles. They spin, they tumble, they have a definite physical shape. Treating a real-world object as a dimensionless little dot, it just fundamentally fails the second it starts rotating. Imagine throwing a wrench through the air. It doesn't just glide smoothly, right? It spins wildly, end over end. To truly understand the real world and to actually solve these exam problems, we're forced to learn a new extended framework, because tracking every single particle of that tumbling wrench is literally impossible. So, how do we solve this? Well, we use a crucial mathematical life raft called the center of mass. By definition, the center of mass, or CM, is the mass-weighted average position of all the particles within a system. This single concept is the ultimate bridge that connects the chaotic spinning world right back to the simple linear mechanics you already understand perfectly. And what's super interesting is how visually striking this mathematical truth really is. When you mathematically track the center of mass of that tumbling wrench, no matter how wildly it spins around its axis, the center of mass glides through space in a perfect, smooth parabola. It moves exactly as a simple point mass would. This rule is so absolutely bulletproof that it holds up even under extreme stress. Think about an internal explosion. When an object shatters in midair, fragments go flying everywhere. But because internal forces always occur in equal and opposite pairs, they cancel out completely. The trajectory of the center of mass remains flawlessly intact. It is totally unaffected by the explosion. Only external forces matter here. Moving right along to section 2, the taxonomy of motion, let's map out the specific categories of movement an object can experience out there in the real world. Knowing how to classify motion is literally step 1 to getting the correct equations on your test. There are 3 fundamental classes you need to memorize. First, pure translation, like a box sliding down a ramp, where every particle has the exact same velocity. Second, pure rotation, like a spinning ceiling fan, where particles move in concentric circles. And third, rolling. Rolling is really just a combination of the first 2. It's the translation of the center of mass plus pure rotation about the center of mass. All right, section 3, the physics Rosetta Stone. We've officially arrived at the grand secret of the universe, and this is exactly where all the puzzle pieces finally lock together. You're definitely going to want to save these next concepts for your study guide, because we call this the Rosetta Stone of mechanics. Basically, every single concept you know from the linear universe has a perfect rotational twin. Displacement x becomes angle theta. Linear velocity v becomes angular velocity omega. Mass transforms into moment of inertia. Force becomes torque. The universe is playing by the exact same mathematical rules, whether you're moving in a straight line or spinning in a circle. It's awesome. Section 4, key formulas explained. The crucial takeaway here is understanding those translated variables. So let's break down the 3 absolutely most important rotational formulas you're going to need. First up, the rotational twin to mass, the moment of inertia, represented by a capital I. In linear motion, regular mass simply resists being pushed, but moment of inertia is an object's resistance to rotational motion, and here is the major trap students fall into on exams. Unlike simple mass, rotational resistance cares deeply about exactly where that mass is placed relative to the axis of rotation. For example, imagine 2 objects on a scale with the exact same total mass. But because the equation for moment of inertia squares the radius, a hollow ring with all its mass pushed out to the furthest edge has an exponentially larger moment of inertia than a solid cylinder. Pulling mass further away from the spin axis exponentially increases how hard it is to get that object spinning. Next up for your notes is torque, symbolized by the Greek letter tau. Just as force is required to produce linear acceleration, torque is the rotational equivalent of force, required to produce angular acceleration. Put simply, you can't make an object start spinning without applying torque. Think about opening a really heavy door. If you push right at the hinge where the radius is basically 0, the door obviously doesn't move. You produce 0 torque. But if you push perpendicularly at the furthest outer edge of the door, maximizing your radius, you maximize the rotational push. That right there is torque in action. Our third critical variable is angular momentum, marked as L. Just as a heavy truck moving fast inherently fights against stopping due to linear momentum, a spinning object has an incredibly stubborn tendency to fight any changes to its current state and its axis of rotation. Take a spinning bicycle wheel, for instance. Its angular momentum factor points straight along the axle. If you want to tilt that spinning wheel, if you want to change the rate of its angular momentum, you have to apply an external torque. This perfectly translates Newton's second law right into the rotational universe. So how do we use this practically? Well, one of the biggest places students lose points is on vector direction. To make sure you never look silly twisting your arm into a pretzel during a final exam, just use the right-hand rule. Step 1. Curl the fingers of your right hand in the direction of the rotation. Step 2. Your extended thumb automatically points in the direction of the angular vector. Imagine physically gripping the vertical axis of a spinning top. The rotation is sweeping around, so your fingers curl with it. What happens to your thumb? It sticks straight up. That hidden, invisible angular vector, omega, points exactly straight up along the axis. Whenever you're dealing with angular velocity or momentum, just use your right hand and you'll always like the direction right on your test, for sure. And finally, Section 5, Advanced Decoupling. For our advanced learners out there, let's culminate this study session by looking at the ultimate synthesis of classical mechanics. We have to talk about the conservation of angular momentum. A spinning figure skater perfectly proves everything we've just talked about mathematically. Because there's no external torque acting on her, her total angular momentum, L, has to remain entirely constant. So what happens when she pulls her arms inward? Well, her radius drops, which means her moment of inertia drops significantly. But because L must stay constant, the universe insists mathematically that her angular velocity omega has to instantly increase to compensate. She spins faster without any extra push. How cool is that? And this brings us to what I consider the absolute triumph of physics. Any terrifyingly complex tumbling, like an acrobat doing a triple flip through the air, can simply be decoupled. You can break that impossible problem into two independent, totally manageable ideas. Pure translation of the center of mass using F equals ma, mathematically added, to pure rotation about that center of mass, using torque equals I times alpha. Two simple equations taming seemingly impossible chaos. Which leaves us with a truly fascinating thought to end our explainer today. If the universe so perfectly and beautifully mirrors linear laws into rotational ones, down to the exact algebraic structures, what other hidden mathematical symmetries are just waiting to be decoded as you move into quantum mechanics and relativity? Good luck on your exams, keep looking for those symmetries, and stay curious.